Hopefully you asked ahead of time, but we do record the talks. We do post them on YouTube afterwards. If for some reason you don't want that, just let us know. Those of you joining us via Zoom, if you don't want your face to appear on the recording, you can turn off your video. And yeah, so we'll get started. Welcome everyone. This is our second season of the VAST seminars. We started with our first talk a year ago in September of last year, and I think we had a pretty good first year. And we've got lots of new things planned for year two, including an expansion into exoplanetary software. And that's going to be the theme of today's seminar, which is the introduction of ExoVAST. Some other things, we are always looking for new talks, especially if you're, a junior colleague in our field who's worked a lot on software development. Maybe you're on the job market and you want to show off all the cool stuff you've done. Go to our GitHub page and raise an issue proposing your talk. And that's how we select talks. We try to do everything out in the open, and we'll post a link to the GitHub in the chat in just a moment. We're going to do two 20-minute talks, and we'll maybe take one question after each talk, and then we're going to have an open discussion. And if you have questions, you can drop them into the chat, and that way we'll get to see what people are asking. And only now I've checked if I'm not muted. So, this is how used to Zoom I am, right? But I'm sure I would have been told otherwise. All right, so it's great to see everyone. As I said, we are starting out with a new track called ExoVAST, which is going to focus on software for exoplanets. And it is going to be led by Joe Renaud, who is here on, I can't see where he is on my screen right now, from University of Maryland and NASA Goddard. And he's going to tell us about the Exoplanet Modeling and Analysis Center, or EMAC, and the idea behind ExoVAST. And then once things get going, as Joe will say, we're going to stagger the normal VAST talks and the ExoVAST talks in each month. So, Joe, I will turn it over to you. I'm not sure we tested screen sharing, so let's just hope it works. Oh, we did.
We did, yeah.
Great. And you can run the show.
All right. So are you all seeing a full screen?
We are.
Awesome. Thank you so much, Michael. Thanks everyone for coming out. So yeah, as Michael said, my name is Joe Renaud, and I'm a postdoctoral associate at the University of Maryland in NASA Goddard. And I've been with the EMAC, the NASA Goddard's Exoplanet Modeling and Analysis Center, for just about 2 years now, and recently was named co-lead of it. And I'm here to introduce EMAC for those of you who are unaware, and also introduce this new idea of ExoVAST. So just jumping right into it. So I wanted to start out talking about ExoVAST. So this is kind of what we're all here for today. This is the regular VAST seminar, the Virtual Astronomy Software Talks. And the EMAC team reached out to VAST, and the VAST team was very great, very accommodating, talking to us about a bunch of different ideas. But we wanted to start a new series that was focused just on exoplanet science, on software and astronomy tools, resources, databases, but for the exoplanet science that is happening around the world. So we thought that the VAST model was great. It's been hugely successful for the past year, and we wanted to kind of do a spin-off of it. So today is kind of the kickoff of this new ExoVAST, where the EXO stands for exoplanets. And this will be a regular seminar series hosted on the first Wednesday of each month. The regular VAST series will continue as usual on the third Wednesday. So I have the dates over there on the right-hand side. So the next VAST will be on October 18th, and the next ExoVAST will be on November 1st and on December 6th. This is kind of a trial period for us. We're trying to see how this goes, but we are definitely looking for more speakers. So you can apply to be a speaker using the same tools that you do for the regular VAST seminars. So you can just go to vast-seminars.github.io, and there's all the information there on how to apply for a talk and also how to join the mailing list to learn about upcoming VAST or ExoVAST talks. Again, I just want to really thank the VAST team. You can see the organizers listed there. All of them have been very gracious working with EMAC and setting this all up. I also want to thank David Rice, who you will be hearing about after my talk, who is the first kind of kickoff speaker of the ExoVAST seminar series. So I mentioned EMAC, the Exoplanet Modeling and Analysis Center here at NASA Goddard, but I haven't actually introduced what that is. So EMAC has been around since around 2017, 2018, but has really picked up steam in the past couple of years. And this is an online category and repository for all kinds of exoplanet-related resources, whether they be code and software or databases or anything like that. And the whole mission of EMAC is to, first off, make sure that scientists that are doing exoplanet research can quickly find the tools and resources they need to conduct that research. So for example, if I'm trying to do a new project on the atmospheres of exoplanets, but that's not really my expertise, I can go to EMAC and type in a few keywords or look at a few categories and quickly find what is the latest and greatest in atmospheric modeling tools that are out there. And then I can reach out to the developers of those tools and connect with them and hopefully do some great science. We also provide a lot of support to both the scientists and the developers of these tools by getting their resources out there to the public, and also with developing new things like web apps and other front ends to make their resources more accessible to the wider public. And we really want to be kind of the first stop when it comes to new projects, especially when you're looking at intermodal comparisons. So for example, if I have two atmospheric models, I have one tool and another one, but I don't know which one to use, I can check out EMAC and see what's been done in the past and see which one is more applicable to my specific problem that I'm trying to solve. So EMAC has been supported over the years by NASA Goddard's Sellers Exoplanet Environments Collaboration, or SEEC, as well as various other organizations in the local DC area, as well as NASA headquarters itself, and the Sciences and Exploration Directorate, as well as the Planetary Science and Astrophysics divisions. So like I said, we launched around 2018. And as of now, we get hundreds of new weekly visitors to the website. And we have over 200 published resources on many different topics within exoplanet science. And just this past spring, we hosted our first developers workshop, which was a virtual workshop. We had over 300 registrants and 40 talks over 3 days. There's a link there to our YouTube. I can also post links in the chat later. But if you check out our YouTube page, you can see the recordings from that workshop, which featured a whole bunch of different exoplanet related tools. And that was kind of the kickoff of this whole ExoVAST idea. That was such a successful event that we wanted to continue it forward. And we thought that a more regular seminar type series like the VAST seminars would be a great way to do it. So we have a very small team here at NASA Goddard. Eric Lopez and I are the new co-leads of EMAC. Avi Mandel is the founder and advisor. We have 2 developers that are handling the front end and back end, Dylan Christie and Mike Moore. And I especially want to highlight Ashraf Dabi, who just started with us this past week as a post-baccalaureate researcher. So post-bacs are folks that have finished undergraduate college but haven't decided if they want to pursue a a graduate degree or go into industry or something like that. So Ashraf will be working with us for the next year on developing EMAC and working with our scientific partners to make the website even better. And he's amazing. We've been lucky, actually. EMAC has had a number of postbacks over the years that have gone on to different industry and grad school. So definitely, if you ever see a grad application from someone who's worked at EMAC, I would highly recommend them. So now I'm going to break off from the PowerPoint and actually show you the EMAC website and how you can interact with it. So just bear with me. Hopefully everything works out okay here. So hopefully you are seeing the actual EMAC website in my browser. Someone just feel free to jump in if you are not. But not hearing anything, I will assume it's okay. So this is EMAC. The website is up on the top. It's also on the slides, which I'll go back to. And on our homepage, you can just right away see all of the different resources that have been submitted. They are presented in these little boxes here that have a variety of information, which I'll get into in a moment. But the real power of EMAC is the ability to search for the specific types of tools that you're looking for. So for example, I'm going to type in title here and hit enter. And you can see all of the resources that have some sort of title dynamic component to them. So I have my own tool up on EMAC here, so I'll use that as a guinea pig. On the box here, you can see the various categories that this falls under, which I'll get into in a little bit. But you can also get a quick introduction to the tool, what its purpose is. You can click on About, which will take you to the tools README on GitHub. And if I go back to EMAC here, we also have this shield system, which we borrowed from ASCL, where you can click on this and copy the image here to post on your own GitHub or website or whatever it is, which can link back to EMAC so that folks can learn more about your resource. There's also a button for the code, so you can go and download the code. EMAC specifically, we try to keep most of the resources that are submitted open source, or we try to accept only open source software. There's a few exceptions, but all of the tools that are submitted to EMAC are definitely open access. So everyone should be able to go to your tool and download it and actually start running models and doing science with it. We would prefer if it was open source so that people can actually start contributing to the tool and making it even better. So talking about the categories here, you see this box with a bunch of different topics, and I can click down on these and they expand into subcategories, so I can do further filtering. So if I reset on this, let it load. I'm going to click on, let's do atmospheric models, let's do retrieval codes, let's do radiative transfer tools and observatory models. So you can see I can select multiple different topics, and it will filter all of the tools that are submitted to EMAC based on that. So for example, we have the planetary spectrum generator here that fits all of this criteria. And this is a good example of a resource that is pretty well built out. It has a lot more features. So for example, it has a demo button here, which takes us to this YouTube tutorial. I won't actually play it here. This YouTube tutorial about how to use this particular resource. And this is actually one of the other things that we are hoping to get out of the ExoVAST seminars is all of these talks will be recorded and uploaded to YouTube. And that way we can link to them with this demo button because a lot of the resources that are on EMAC right now don't have these types of tutorials. So for example, David Rice's resource that he'll be talking about later in today's talk, that'll be uploaded and we can link to it so that if somebody wants to learn about how to use that resource, they can just check out his video. There's also the option to go over here to the web app. So this is the web app for planetary spectrum generator. So you can see this particular tool models the expected observed spectrum for exoplanets and all kinds of other things, like they have different like Jupiter, all kinds of stuff here. I'm not going to go into PSG specifically, but it's one of the more popular tools that is hosted on EMAC. So categories is great. You can learn a lot about what resources are applicable to your specific project, but we also have a few new types of ways of searching for tools. So if I reset on this and go to resource types here, so this is a listing of the different kinds of resources that are on EMAC. So there's ones that have tutorials, ones that have that are more specific for inter-model comparisons or catalogs and databases. So all of these things can be used to further filter what you're looking for. And then the last one here is collections. And this is a new system that we're using to combine resources that are applicable to certain different kind of major topics. So as you see here, a lot of these are just different observatories. So JWST has been hugely popular in the past couple of years with its successful launch. So if you want to see all of the resources that are used to analyze JWST data or make predictions about what JWST is going to observe, you can click on this. There's also some subcategories here that if you want a further refinement, and you can check out what resources are available. Now, something that we are really trying to do here, you'll see this word curators, which just has the EMAC team. One of our asks for today to all of you, the community of astronomers and exoplanet scientists, is that as you saw, EMAC is a pretty small team. We only have a few members and we all have expertise in exoplanet science, but we don't have expertise in everything. So we are really looking for new volunteer curators that can join our team and help us both find new resources and put them into these buckets so that other people who go to EMAC can quickly find these things. So I'll talk a little bit more at the very end about this, but if you are interested in becoming a curator for EMAC, especially if you have expertise in one of these categories, or if you have expertise in one of these missions, for example, definitely get in touch with us. For everyone else, if you don't want to be a volunteer curator, but you happen to have developed a resource in the past and you want to see it up on EMAC, then you should definitely submit it. So to submit a resource, there's a button here that you can click and you can provide some basic information about yourself and your resource. And I would highly recommend scrolling down here and clicking on these additional resource details, because this really helps the EMAC team categorize what collections and what categories your resource should fall under. So they're kind of hidden right now, but I definitely click these to expand so you can check these off, and that'll really help us make sure that people are finding your resource as easily as possible. If you don't have a resource, or if you've already submitted a resource to EMAC, but you want to learn about new resources, we have a subscription system where you can go to the subscribe button here, put your email address, and then you can check off what categories you're interested in. And whenever there's a new tool posted to those categories, you'll get a notification, and you can change how often you get these, whether they're immediately or weekly, etc. I'm not going to go through all of these pages here, but I definitely encourage you to check them out. But the last one I will show is this new one that came out of our workshop that we had this past year. That's a for developers page. And this just is a place where we as a community can just throw up any helpful resources or information, guides, etc., on how to make open source astronomy software, especially as it pertains to exoplanet science. So it's pretty bare bones right now. If you have a really good resource that you want to share with the community, or you have some really good tips and tricks on how to develop open source software, get in touch with us, and we'd love to see this expanded in the future. All right, so almost at the end here, I'm going to leave the live demo portion and go back into the slideshow. And just end on what's next for EMAC and for you. So like I was saying, if you want to see your resource on EMAC, I definitely encourage you to submit it. If you have colleagues or other people in your departments, tell them about EMAC. Get the word out there. Tell them about the subscription service, and tell them about ExoVAST and VAST itself, and get them on the mailing list so that they can learn about that. If you have any suggestions or questions, the general EMAC email is up there, as well as my own personal email. EMAC is EMAC, along with the rest of the world, is trying to navigate the new social media spectrum, but we still have an account on the old Twitter that you can follow. So feel free to follow us there and learn about updates to the website and repository. And again, the big thing that we're trying to push right now is to get more volunteer curators, because right now everything is kind of being done in our voice. So if I have expertise in planetary interiors, a lot of folks on the team have expertise in planetary atmospheres, but if something doesn't fall into those categories, it's hard for us to capture it. So if there's a really awesome stellar astrophysics tool out there that's applicable to exoplanets, it might not be on EMAX just because we don't know about it. So we're really looking to expand our expertise on the team. So if you are interested in volunteering and helping us collect new resources, get in touch with us. But I think that is it for me. So I will turn it back to Michael, and thank you all so much. I'd be happy to talk about EMAX some more later, or answer any questions. Thank you.
Thanks, Joe. It occurs to me there's an Emacs versus VI joke in your name somewhere, but I'm sure you've heard
yes, that's definitely true. We're EMAC without the S. Trust me, I got a lot of grief when I first joined the team because I kept saying Emacs just in general. I probably said it a couple times in that talk just then, but EMAC without the S.
Yep. All right. And I should note that at the moment, and probably going forward, we are using the same GitHub talk proposals repo to submit talks for both regular VAST and ExoVAST. So if you want to submit a talk there, you can go ahead and do that. You can apply a label that says, I think it's either ExoVAST or EMAC, I can't remember, to your talk proposal, and we'll take a look.
Yeah, it's ExoVAST.
It's ExoVAST. Okay,
yeah.
Cool. We don't have any questions on the chat right now. So I think what we'll do is we'll move on to our second talk, and then we're going to have our open discussion as we planned. So next up, we're going to hear from David Rice from Open University Israel. David, are you joining us remotely from Israel? Is that?
Working remotely from Vegas still for this year.
Oh, okay.
Had an awesome opportunity to stay in the United States for a year, but hoping to move there next year.
Ah, okay, cool. Because I was going to say the time zone must be quite different.
It's only 9 p.m. there, so.
Ah, okay. So David is going to tell us about solving and visualizing planet interiors with MAGRATHEA. I want to say margarita, and then I think about pizza, but all right. So let's hear from David.
And you can hear me, okay?
We can hear you great. We can see. Well, right now we see your full screen.
Full screen. Oh, did that switch?
We see presenter mode.
Yes. Okay. So presenter view. That better?
Yep.
Awesome. Hey. All right. Well, thank you to the ExoVAST team for having me. Great talk, Joe. Thanks for the introduction, Michael. Excited to see the VAST series continue, and especially this exoplanet specific weeks, and excited to be one of the first talks on exoplanet specific weeks with my code MAGRATHEA. MAGRATHEA is a planet interior code which has been hosted on EMAC now for the year since it's been published. EMAC has been a great tool to publicize the code and share it with other people. And I developed the code along with Chenliang Huang at the University of Nevada, Las Vegas. And Chenliang was a postdoc, and I was a PhD student here in Las Vegas. Chenliang's now faculty or staff at the Shanghai Observatory, and we were advised by Jason Steffen here at UNLV. Now we're both moving on, but we're both developing MAGRATHEA still while working on some other projects. I'm now at the Astrophysics Research Center of the Open University of Israel, advised by Alona Vazan. So I'll be talking about our code MAGRATHEA. So I think we've probably all been there. We've got a planet. We've got maybe the mass and radius. Maybe we have some surface properties. Maybe we know something about the interior here in the solar system. And we've all wanted to just cut it right open and check that it's not cake and see what's inside of this planet. So that's a very funny little explanation of it. But our solution to this problem of figuring out what's inside of a planet is MAGRATHEA. So here's highlighting some aspects of the code. It's an open source planet interior platform. So although we have a default model, we've really tried to program it so you can build your own model for whatever type of planet you want to solve. We publicized it in Huang, Rice, and Stefan 2022. MAGRATHEA is the fantasy planet from Hitchhiker's Guide to the Galaxy where they build other planets. So it's not any weird astronomy acronym. It's just MAGRATHEA. It's written in C++. It uses shooting to a fitting point method. That's just to say it's wicked fast. It takes about 1 second to run a planet. Although I use it mostly for terrestrial planets, it's extensible. We can do sub-Neptunes with it, mini Neptunes, even up to Neptune. We just need to think about where these equations, if you provide the equation, we'll solve it. We want to think about where these equations should be used within these planets. And many of these parameter spaces, we don't have better equations for. And it's also transparent, which I'll talk about a lot in this talk. So just a quick explanation of a planet interior structure model. These have been used since 2004 with some of the first works listed down in the bottom for exoplanet science. Planet interior structure models generally are one-dimensional, spherically symmetric, fully differentiated shell models. So we solve in each one of these shells the equations of hydrostatic equilibrium. Here, including an isentropic temperature gradient is the default. We can do some other temperature gradients within that planet also. You put the total mass in each of these differentiated layers, and we get out the radius, the pressure, the density, and the temperature here all with enclosed mass or with radii. And the problem or the interesting thing about planet interior structure model versus like a star structure model is equations of state. Is you have a lot of different compositions within your planets, and we need to know how all of these materials respond to pressure and temperature. So while some of the first models use just one composition for each of these differentiated layer, what you really want is a phase diagram within each layer. So what your mass you're inputting tells you which layer you're in, but then once you're inside a layer, the pressure and the temperature determine what composition and what equation of state you're using. So these are the default phase diagrams of MAGRATHEA for the core, mantle, hydrosphere, and we have an ideal gas atmosphere. We've got that hexagonal closed-packed iron in the core, along with liquid iron, these phases of magnesium silicates in the mantle, along with silicate melt, and these high-pressure ices, along with liquid water in the hydrosphere. In this equation of states library, and these phase diagrams are ever expanding in the code. Focused on these equations of state, each one of these materials, we need measurements of how they respond to pressure and temperature, ideally laboratory measurements. And that's really what inspired MAGRATHEA for us, is we wanted to get in this interior game because downstairs in Las Vegas, we have a high pressure physics lab, and we wanted to take their materials they're crushing in diamond anvil cells and put them into planets. And we realized there was really no open source software in order to do this. So that was our motivation. And to do that, we have a lot of these imperial equations of state. So this is the Birch-Martinham third order equation of state. You can see the bulk modulus here, the reference volume, the derivative of the bulk modulus. These are all things high pressure physicists determine for their materials. Bulk modulus is the resistance to compression of the material, or 1 over the squishiness. And we have 6 different formulations for these equations of state. So all these different fitting formulas of how these materials respond to pressure, also how these materials respond to temperature. So this is a Debye thermal pressure determined by the Greneisen parameter, and we have 3 different formulations for the temperature of these materials. So that was a super fast explanation of what MAGRATHEA does. I'm not as daring as Joe, so I'm not going to do a live demo. This talk will force me to put the tutorial. We have the paper describes the code. We also have a great description on our GitHub. I also developed a tutorial for Rocky Worlds Conference that I've been meaning to put on the GitHub. So this will force me to do that. But what I wanted to focus on in this talk is showing you a bunch of graphs. So a bunch of ways to visualize these outputs from MAGRATHEA, which will highlight different aspects of the code and hopefully inspire you to analyze an interior yourself and see how they're responding or how these planets look in the inside. So this first graph, this is kind of summarizing all the things you get out of MAGRATHEA when you put a planet in. So the top is planet 1. This is a 1.1 Earth mass planet with a thick hydrosphere. It's got 0.3 Earth masses in the hydrosphere in the water, 0.4 in the mantle, and 0.4 in the core. While planet 2 is a more Earth-like planet. It's a 1 Earth mass planet with this 33% core and 67% mantle. Starting the mantle hot here. So this graph is pressure on the x-axis going inside to the right, and temperature increasing on the y-axis. The dots here are each of these solutions at adjustable step sizes of enclosed mass that MAGRATHEA solves for. So you can see the mass increasing from 0 inside all the way up to the planetary mass on the outside. And as the MAGRATHEA shoots for this solution, it follows the isentrope of temperature through these different compositions. So the top planet starts in water, goes through these high pressure ice phases, ice 6, ice 7, ice 10. We can put temperature discontinuities between the layers. So we see this temperature discontinuity in the Earth between the mantle and the core. So we want to be able to simulate those if you want them into your planet, or you can keep them all at thermal equilibrium and not put a discontinuity. But for these to demonstrate, I put a temperature discontinuity between the layers. So it jumps up into Bridgmanite, post-perovskite, this high pressure silicate, and into hexagonal close pack in the core. While the Earth-like planet, instead of having that hydrosphere, has these lower pressure magnesium silicates, this forsterite, wosleyite, and ringwoodite, into the Bridgmanite, into the post-perovskite, into this HCP iron, and it even has a small layer of melt on top of that iron core. So that's a basic MAGRATHEA output. And with all of these materials, what we wanted to create is what we want to show is just how many parameters go into these works. So the top planet has 65 parameters from 8 different works, how these materials are responding to pressure and temperatures, and their phase and the transitions between the different materials. And the bottom has 48 parameters from 7 different works. So in MAGRATHEA, we created a library of all these planet materials and measurements for different materials. So we can recreate the planets from Siegert 2007 work, or you can use the most up-to-date physics and geology measurements of these materials. So this is a mass radius plot with some lines of isocomposition on it for 100% water planets, 100% mantle planets, and 100% core planets. And here we're just changing which material or which measurement for the material is the dominant one in each layer. So on the top is 5 different measurements of water ice. The purple line is if you don't include ice 10 in these planets, which some earlier works did not have measurements for ice 10. You can see that quickly creates planets up to 5% difference in radii. The mantle planets have some different measurements of Bridgmanite and post-perovskite, and the core has some different measurements for hexagonal close-packed iron that can create planets up to 2% difference, and 2 iron silicate alloys, which can create planets up to 5% difference if you're lightening that core with some silicate inside the core. I want to highlight here that we have new measurements from UNLV physicists. So in Wang-Rice et al. 2021, we took some new measurements for ice 7 and ice 10 from UNLV physicists and modeled planets with them. And I also have a high school student adding equations of state to the code. So Sri is looking for college right now. He's applying, but he added all the materials from Sticksrud and Lithgow Bertoloni 2005, which is this massive table of mantle materials. He's added those all to the code. So this is a big library we have that you can easily swap in and out equations of state into your phase diagram, change your phase diagram around to see how this planet responds to these different measurements. And I just wanted to show this is the only code I'm going to show it. Then it's back to all graphs. So these are two different measurements of iron HCP, the transparent storage structure we have in the code. So this in the equation of state list.cpp. We've got two measurements, one from 2013 and one from 2017. 2013 was a experimental work, while 2017 was a compilation of some different works. And these both use different formulations for the equation of state. So this 0 parameter here, we have all these parameters tabulated in the paper and the GitHub. The first one uses a Hausepfel equation of state, while the bottom one uses a Renaud equation of state. And you can see the bulk modulus here, equation 2, or parameter 2, differs by 100 GPa. So this is 100 gigapascals difference on how, in these formulations, this material responded to pressure in these two different works. So they often don't even overlap to 1 sigma, these experimental measurements. So back to the graphs, done with the code. All right, I've got like 8 graphs to show you for the rest of the time of just cool things you can make with MAGRATHEA. This is all of the small confirmed planets with under 10 Earth masses, with some cutoff for the temperature and some cutoff for the uncertainties, that have both masses and radii measured. And we've plotted curves of isocomposition on this bulk density plot with mass on the bottom. So these aren't independent measurements, but you can see these different groupings of iron-rich planets, mantle-rich planets, and water-rich planets, and even planets that require some atmosphere. So you can make these mass radius curves, provide a small document of masses and different and isocomposition, and MAGRATHEA will solve it in just a few minutes. One of my favorite things to make is ternary diagrams. So you can make a ternary diagram in the code in just an hour. This is the radii of 1 Earth mass planets. So with these 3 different components, mantle, water, and core, this is all the radii you can get for 3-layer differentiated planets of 1 Earth mass. So Earth is down here at 33% core and 67% mantle. You can see this blue is about 1 Earth radii. And then all the planets along this blue curve have the same mass and radii of Earth. So you can get, as you increase the core, you increase the water to keep that bulk density the same for the planet. And one thing I've done is now thinking about that line of constant mass and radii, we can make a composition finder. So for a given planet, we're going to translate this weird ternary diagram looking thing into a more normal plot. So we can think about a ternary diagram that the bottom axis is the core to mantle mass ratio. So as you swing one of these lines over, this dashed line, as you swing it over from one side of the bottom to the other side, we're going to define that as the RCMF. So the RCMF, the refractory core mass fraction, is a core divided by the core plus mantle. So you can think about it as the iron to silicate ratio, or the iron plus over the iron plus silicate, although the composition could be different. And then going up on a ternary is the water mass fraction, at least in this rotation. So the weight percent of water on the right plot is the y-axis, and there's no weird forbidden regions on this plot. All of these planets are possible. Here on the dashed line are all planets that have the same iron to silicate as the Earth under the water layer. So as you increase the water layer, then keeping the core to mantle ratio the same on that dashed line. So if we take a mass and radius of a planet, we can then solve for all the different planets that for 3-layer compositions that match that mass and radii. So here we have a composition finder in the code that you swing across refractory core mass fraction. And then the refractory core mass fraction gives you your core and your mantle masses. And then you shoot for the water mass fraction that you need to match the radii. So those 3 masses, and then shoot for the radii, shoot for the water mass fraction to give that radii. So all the planets along the blue line here have the same mass and radii. You can see down here at low, when you have no core and just mantle, you need very little water for this planet. And then as the core increases, you need more water to make up that higher density core. You need more water to make up that radii to still match that mass and radii that you've measured. So my my work is focused right now on TRAPPIST-1F. This is what happens if you take now 5,000 measurements of mass and radii here from AGL 21. TRAPPIST-1F is this amazing one Earth radii, one Earth mass planet. Taking 5,000 measurements, swinging it across 101 refractory core mass fractions, and then solving for the water mass fraction to match that mass and radii is 5,000 blue lines across here. This is 2.5 million runs of MAGRATHEA. It takes just about 2.5 days on 12 cores, which is relatively short compared depending on your computer resources. But all the planets here in the blue are possible for TRAPPIST-1F. We have the median here in light blue and the 1 sigmas in dashed lines. And we can pick out some planets on here. So if you're at an Earth-like RCMF, so Earth-like core to mantle ratio, then you would need about 6.5. On average, you would need 6.5% of your weight in water. We can also ask if TRAPPIST-1F is dry, if it has no water at all, then it means it has to have a small core. It means it needs only a 14% core mass fraction. And one fun thing we did, also with that high school student, is we took MAGRATHEA outputs. If we take these 2 planets, solve it through MAGRATHEA, look at the structure file, actually looks at the solution throughout this planet, we put those into Blender. So Blender is a 3D modeling software. And we can take a MAGRATHEA output automatically, putting a shell at each radii and then coloring those shells with the correct color for composition. So these are 3 different possible interiors for TRAPPIST-1F. The side here is kind of that median profile at an Earth-like RCMF. The top is a Mercury-like RCMF, so a massive core needs a massive hydrosphere to match that radii. And the bottom is a dry planet, so it has a very small core. You can't even, the core gets cut off here in the picture. So we can point out those different materials. The iron here is gray. The green is all these mantle rocks. Mantle rocks are made with olivine, so they're green here. The dark green is a post-perovskite phase at high pressure silicates. We've got light silicates on top, while the planet with a massive hydrosphere doesn't have those lighter silicates. Instead, it has that high pressure ice at the bottom of the hydrosphere. So it has ice 10 at the bottom of the hydrosphere. So that's a fun thing we have in a separate GitHub. You can see in github.com/davidrwright/blender-magrathea. It's a fun thing to do. And also looks great in papers too. So you might be wondering about bigger planets. TRAPPIST-1F, amazing measurement. We can do bigger planets if you put the right caveats to it. Here in McDonald, Fail, Quinn, and Rice 2022, I found the compositions of K2-138b through E. That work is focused on finding the resonant, confirms the resonant structure of K2-138, and then uses that resonant structure to confine the masses by just a little bit. So we solve the composition and we find K2-138b can be solved with the 3-layer water mantle core planets, while the outer planets really need an atmosphere to match those masses and radii. So on the right here is a mass percent of water. So we've picked some core to mantle ratio underneath, and then solved across water mass fraction here on the x-axis for the atmosphere mass fraction to match these masses and radii. So you can see C and D here have possibly very similar atmosphere mass fractions, while E requires a much larger atmosphere mass fraction for these planets. And 20 minutes, one more plot for fun is this is the water worlds from Luke and Palais 2022. So Luke and Palais 2022 reanalyzed 9 planets around M-dwarf stars, significantly improving the mass and radius uncertainties. And they found that they kind of lie on these 2 tentative lines, provocative lines, of one line being a 50-50 water to mantle ratio, and one being a 67-33 mantle to core ratio, like the Earth. So an Earth-like line and a water world line. So these are those 9 planets with isocomposition lines from MAGRATHEA, a mass radius line here, along with TRAPPIST-1F. You can see how amazing the uncertainties on TRAPPIST-1F are. And one thing I did with this is we take all of those different mass and radius measurements, do the same thing with TRAPPIST-1F, solve for all the possible 3-layer interior structure for these planets, And then we can summarize those 3-layer interior structures into an uncompressed density. So taking all of those simulated planets that match the mass and radii of these planets and then uncompressing them. So take however much material there are at room temperature and room pressure, what would the density of the planets be? So this is a interesting graph to think about that I probably don't have time to talk about completely here, but we've got uncompressed density on the Y and bulk density on the X. You can see Earth here is at 1 bulk density relative to the Earth and about 4 uncompressed density, so 4 grams per centimeter cubed. And these planets all lie below that Earth line because they have solutions that could have water on these planets. And they look a little bit different in this parameter space. So we've analyzed the peakiness of these 2 distributions. So that was some graphs that I hope inspired some interest in MAGRATHEA. I'm completely available for collaboration and communication. I can provide some tutorials and some more help. Currently in development with a couple different groups that are using MAGRATHEA is we're finalizing that composition finder and analyzing observed planets. We have a couple of groups analyzing observed planets with the code, expanding that equation of state library, putting in mixtures. So we have a rock ice mix in Alona Fazan's group. And I'm also working, my current project is working on ideal mixing all throughout the planet. Also putting an entropy function for temperature. So not only isentropic, but you can put in an external entropy function to solve the temperature throughout the planet. Some ideas, MAGRATHEA is great for undergrads, graduate students, your own research. I say you can get an undergrad up to speed on it in just a day, maybe a week for undergrads, but 1 grad student afternoon, you should be up and running with MAGRATHEA. Some ideas is to put a non-ideal atmosphere, 3-dimensional PVT table interpolator has been on the top of the list for a long time that we haven't gotten to. Improved water layer, couple to atmosphere model, couple to a thermal evolution model. I've got all kinds of ideas of things that need to be developed for MAGRATHEA, and we encourage the community to contribute, and you can become a MAGRATHEAN here at the link. So thank you for your time and for listening.
Also,
Sorry, go ahead.
thank you. Oh yeah, thank you for your talk. And I think what we'll do now is we're going to turn things over for the questions, and Sam is going to run the questions.
Yeah, sure. So yeah, there are some questions in the chat already, and if you have more questions, feel free to add them to the chat, or you can raise your hand in the, however you raise your hand, and I can call on you. So the first question is from Michael, and it's, is the EOS in MAGRATHEA something that we could extract to use in a multi-D hydrocode?
Multi-D hydrocode. Yes, I would love to link MAGRATHEA to SPH and crash some planets together. It would be super fun. And yeah, we have a function built in the code where you can make your phase diagram and it'll output the equation of state at some given pressures. It needs updated so you can output it at pressures and temperatures. But right now you can output them at pressures. So we should put that temperature in there too. But we have a built-in function to output equations of state.
Okay, great. Next is from Joe, and he asks, when will MAGRATHEA be integrated into Starfield?
I think you can skip Joe's questions.
You always skip my questions.
I gave a talk on Astronomy on Tap. I started the Astronomy on Tap in Las Vegas, and I had a guy who does virtual reality. Like his whole thing is making virtual reality a thing. So would love to get a website developer and run this through a website too. Would make it a lot easier. That would be fun.
Okay, good to know. Next question is from Avi Mandel, and asks, I've heard quite a bit that much of Earth's water is not at the surface, excuse me, and rather dispersed in the core and the mantle. Is this an uncertainty factor for these models, and how is that handled?
Hey, that's a great question, Avi. For the Earth, it's still a very small percentage of water. It still has very small effect on the Earth's interior, affects the temperature gradient some, but we're still talking about way less than 1%, 0.1% of the mass in water. As we have been thinking about mantle hydration, there's a couple works on mantle hydration with interior models out there. Dorn Group has a couple. And it's really exciting. You can pump up the radii by putting some water inside the core, and that's what my postdoc is largely focused on is ideal mixing. So you can mix different equations of state together throughout the whole planet. Really will be this next level of interior models in the future.
Okay, great. Let's see what else. Okay. Joe's got some good comments. So Michael says he was particularly interested in modeling mantle convection in multi-D.
Yeah, that'd be exciting.
Yeah. Okay. Good deal.
Yeah, all those. Yeah, we've been thinking about thermal evolution. A lot of works with thermal evolution ignore material properties, and that's something we care a lot about in MAGRATHEA. So it'd be great to test out those different materials in those convection codes.
Gotcha. Okay, so we have about 8 minutes left, maybe like 6 minutes for discussion. And so if we just open it up to general discussion, and start out with a question from Michael. It looks like it's specifically for Alice and Joe, asking how do EMAC and ASCL interact?
Yeah, that's a great question, Michael. And I did mean to mention this in the talk earlier. I'll just say a few words and then I'll pass it over to Alice. But one of the things that we've worked on this past year, so ASCL has been an amazing project run by Alice for, I believe, the past like 100 years, it seems like, but of cataloging, kind of like EMAC does, cataloging different astronomy tools and resources, but for all of astronomy. And one of the things that we've been working on together over the past year is actually connecting with ADS, which if you're not familiar, ADS is basically like the search engine for all of astronomy science to find papers and tools and all kinds of stuff, to make sure that codes that are on EMAC that developers haven't published a paper for yet, or haven't, like just published them in some way, it's very hard to cite them. So in order to cite things in a scientific paper, you're usually citing some sort of DOI for a paper or an abstract or something like that. But for a lot of the codes that are on EMAC and ASCL, they may not have papers to cite. But what ADS does is it can scrape ASCL to get to find out about these new resources, and then it can provide a way for people to more easily cite the work and reference back to it. And we are working with Alice on making sure that the tools that are on EMAC, but for whatever reason are not on ASCL, still get connected in some way. But yeah, Alice, is there anything else you want to add to that?
Sorry, hold on.
No worries.
I was just trying to. We have an error in something here. Okay, MAGRATHEA entry is not on ADS, so that's something I need to fix, obviously. So yeah, what Joe said.
Our ADS still messed up. Sorry.
Yeah, I'm getting a
Joe,
404.
I've submitted that like twice. You said you fixed it.
Okay, so I will I'll be talking to ADS today. So yeah.
I'll put it in the chat.
Yeah, thank you. So as Joe said, the ASCL it covers all of astronomy, but what we're particularly interested in, and our whole thing is software. We do only software that's available, that's accessible. It may not be open source, but you should be able to see it and read through it. And what we want is the source code itself. So if somebody has a very nice web tool, but you can't see the code behind it, we don't register it. So we register codes. We can also serve as a repository for them and do for for some other codes. And in fact, that's how the ASCL started. But we're trying to improve the discoverability of software, and EMAC has about 77% of the entries in EMAC are software resources. So we want to help expose those, and one way to do that is to have, in some way, an ADS entry for those codes. And we'll be working, we haven't submitted a proposal yet, but we've talked about submitting a proposal. The ASCL needs some funding or volunteer development services, if anybody wants to volunteer to do this, to modify the ASCL so that we can point also to EMAC, just as EMAC points to the ASCL. We'd like to make that reciprocal. So if you've got codes that you've used in research, so our criteria are a little bit different from EMAC's. So we may not be able to register everything in EMAC because we're focused on software, and the software has to be used in refereed research or in research submitted for refereeing. And there's some important exceptions to that, but in general, that's what we want. So there can't be quite 100% reciprocity there, but we can get pretty close. So, and we'll be working on that. So we love, I love what EMAC has done. That's, and he keeps saying small team. I'll have a word. So, and I've been working on ASCL since 2010, and it does seem like 100 years sometimes. So thanks for the question. And I'll turn it back to Sam because I see other questions.
Yeah, there are some other questions in the chat, but we have about 2 minutes left. So if you could maybe ask those questions to David or Joe elsewhere, because I want to be mindful of everybody's time and all of that. And so for the last 2 minutes, I just want to hand things back over to Michael to close us out for today.
Yeah, all right. Indeed. So David and Joe, do take a look at the questions in the chat, and maybe you can answer there. Oops, I didn't start my video. So thank you, both of you, David and Joe. We look forward to seeing how ExoVAST develops. Remember, the model going forward is that I think starting in November, the two series will run 2 weeks apart. So we'll have continue to have VAST every third Wednesday of each month. And everyone is encouraged to submit talks. And in particular, we always try to highlight the work done by junior researchers. So if you're in that, if that fits your description, do propose a talk so that we can give you an audience and hear about the great work that you all are doing. Next week, we have 2 talks on next month. We have 2 talks on general relativistic hydrodynamics codes, one by our own Sam Dunham, who joined us as an organizer this year. And so we're going to look forward to those talks. Our November is currently free. So we're going to start putting together our schedule for the rest of this year. So do get your talk proposals in so we can consider you for those spots. That's all I have. So thank you, everyone, for joining us, and we'll see you all next month.
Yeah, thanks everyone for joining, and make sure to save the date for the next ExoVAST, which will be on November 1st, the first Wednesday. And take care, and thank you so much for the VAST team and Michael for hosting and Sam for the questions.
Sorry, wait, one last question from someone. Where will this be?
No, I have lunch.
Nope.
Oops, sorry. Where will this talk be posted? Which YouTube channel or site or whatever?
We have a VAST YouTube site, and all the talks are always linked to off of the main VAST webpage, which I'll post again if I can find the chat.
And the video may appear in 2 places. That's something we haven't quite worked out yet, is how to handle the videos for ExoVAST. Yeah.
But yeah, if you stay on the, if you get subscribed to the VAST emailing list, that'll be the best way to learn about where stuff will end up. Sorry, Michael, didn't mean to cut you off.
Yeah, and we'll make it clear on the website. We've been discussing how to transform the website to handle ExoVAST in parallel with VAST. So we'll make it clear where everything's going to be shared. But for now, this one will be posted on the main VAST website and maybe somewhere else.
And thanks very much to Joe and David for their presentations. So good job.
Thank you. Thank you. Well.
Thanks, all. All right, take care.